Before we jump into the course, I would like to take you back in time a little bit, all the way to 1980. In fact, what was happening back then is that the Voyager 1 spacecraft, which is on a mission now for over 40 years, which is amazing, back then it was passing by Saturn and it was making observations there. And Carl Sagan proposed the idea of turning it around so it can take a picture of Earth. He knew that the picture would be pretty small and there wouldn't be much scientific purpose to it, but it would give people some perspective. And so it actually took 10 years to happen. On February 13th, 1990, the cameras warmed up for about 3 hours and the observations began from a distance of about 6 billion kilometers. The Earth images were taken just 34 minutes before Voyager 1 powered off its cameras forever. I wanted to start off with this story because I wanted to give you a bit of perspective and context what we're talking about here. By the way, this is Voyager 1, the Beauty. It's been on a mission for over 40 years now. So this thing and the entire program is older than I am. And so we look at this picture, and every author, every poet, every lover, every maniac, every warlord that ever existed that you know of exists on this one tiny pixel over here. And this is Earth, suspended in the vastness of space. And in fact, this whole picture here, this is all just a tiny, tiny fraction of the entire universe out there. So it makes you feel kind of small and humble. And when we talk about things like significance, perhaps we are not as significant as we'd like to think we are. Hello, my name is Evgeny J.C. Golubev. I have a bachelor's degree in multimedia. And while I am not technically a scientist, I consider myself scientifically literate. I often take climate change courses online, and some of them actually require you to write a short scientific paper that gets peer-reviewed by the students of the course. This is a great thing. I really recommend you go through that so you kind of get the experience. And this is to get the certificate, by the way, which you have to pay a little bit money for. The other cool thing about these courses is that people there, admins of the groups and fellow students, will often guide you to active climate change Facebook groups. And in some of them, actual climatologists are posting articles from time to time. So you can have direct access to them if you have any questions, if you have any queries. In general, you can go ahead and ask them a question. I'm sure they'll be more than happy to respond. So I really recommend you go through that whole process and you kind of join the right Facebook groups. Now, I'm not technically a scientist, but actually I consider that to be somewhat of an advantage, and I'll explain why. So when you talk to a scientist, sometimes what can happen is that they start to use very complicated terminology. They use, mathematical formulas, etc. And to the average person, this can feel very intimidating and very overwhelming. So I will explain the topic to the best of my ability in very easy to understand terms. I'll give you one example here. When we talk about climate change, sometimes you'll hear this word, anthropogenic climate change, and you're like, what the hell is anthropogenic? Why do they use these words? Do they have to use these words? They don't have to use these words, but they use these words because, they have a certain reputation to maintain as scientists. They have a certain level of culture, let's say, they have to maintain. So I will try to use very common language so that you can understand. I want to start off by saying that climate change is not super difficult to understand. Definitely the basics of it are relatively simple compared to something like astrophysics, for example. Just to finish off my story very briefly, I used to host a podcast show called Age of Reason, and I think the last 25 to 30 episodes or so were exclusively dedicated to climate change, so please check it out. I took some articles from the media and I shed light on them. In general, my impression is that mainstream media does a pretty lousy job at talking about climate change issues, so I wanted to do a show about that. And it was relatively successful for what it was for. Finally, I wrote some books. Check them out on Amazon. They are not on climate change, but they do have climate change elements in them. So every bit will help me. Thanks a lot. So I called my course EPIC, and EPIC is an acronym here. It stands for Education Information, Personal Responsibility, Innovation, and Community. And these four things together are very powerful, in fact, in how we respond to the existential threat that is climate change. And I will explain these later over the course. So, first of all, I want to start by saying that scientific skepticism is a healthy thing. The reason for that is very simple. If everybody just went around making claims with no evidence, we would have a very chaotic world. So, to have some degree of order, we use what we call the scientific method, which I will talk about in a moment. And we apply a healthy dose of skepticism. So, a healthy dose of skepticism a day keeps the nuts away. That's what I say. Scientists should always challenge themselves to improve their understanding. Yet, this isn't at all what happens with climate change denial. The climate change deniers vigorously criticize any evidence that supports man-made global warming, and yet they embrace any argument that refute it. And personally, I find it extremely ironic that they do that. They deny the science of climate change, and yet they embrace very easily and openly the evidence, quote unquote, of the opposite. They rarely double check the information, and I have never once talked to a denier who actually made any sense. So, while we're talking about large scales, I just want to introduce you to planet Earth. We'll talk about planet Earth a lot over this course, of course. And if you look at the interior of the Earth, you got the inner core, the outer core, and then the mantle. And actually, just these three parts, they make up about 98% of the Earth. Okay, so again, it makes you feel kind of small and very humble. Then you got the upper mantle and the crust, which, depending on measurements, is about 100 kilometers thick. And we live on the thinnest portion there, which is the crust. And then beyond that, you got the atmosphere. So again, it has many layers. And so here, what happens is that the atmosphere typically ranges between 350 to 450 kilometers. But I've read some estimates which even put it at 800 kilometers. So I guess it depends how you calculate it precisely. The International Space Station, the ISS, is around 330 to 410 kilometers in the air, depending on the orbit. But most of the action for us people happens actually very, very low. I would say between sea level, which was 0 kilometers, to about 15 kilometers. Even at that altitude, it becomes already very, very hard to breathe, even impossible to breathe. That's why in airplanes, they need to recycle the air so you can breathe. But people who climb Mount Everest, for example, carry oxygen tanks. And even Bolivia's capital, La Paz, is high enough to cause breathing difficulties, and that's only about 3,600 meters above sea level. So, when we talk about climate change, we're talking about greenhouse gas emissions, and where does it all actually end up? Well, usually it's in the area, in the layer, which we call the troposphere. It's roughly between sea level and 20 kilometers in the sky. Here, it's very interesting to note that ozone at the mid-troposphere actually destroys pollutants, while at the top of the troposphere, it acts as a greenhouse gas, trapping heat. And the ozone layer is an interesting example because I think this was the last time that humanity really kind of came together to combat an environmental threat. And I'm still waiting for this kind of action to happen when it comes to climate change. So we'll see how it goes. So we looked at pretty images of the Earth's interior. We looked at the atmosphere. But how do we really understand any of that? Well, to do that, you need a scientific method. The scientific method is straightforward and robust, but it's not infallible. First of all, you have to formulate a question, and then you do background research. And from that, you construct a hypothesis. Finally, you test it with an experiment. If the procedure is working, you go on, you analyze the data, and you draw conclusions. And if the results align with the hypothesis, you need to communicate them. If all is well, this will undergo rigorous scrutiny by scientific peers. This is absolutely normal. And in the end, you may publish your paper, But when you do publish your paper, it's still not finished because more people will read it and try to find holes in the theory. So you may have to go back and readjust some parameters. If the procedure did not work, you will need to troubleshoot it, like we'll troubleshoot a computer problem when they arise. And by the way, this never worked for me in Windows. You go back to doing more tests using experiments. If the results do not align at all or even partially with the hypothesis, you go back to constructing a new hypothesis. The data you have accumulated so far may or may not be useful. You may be able to reuse some of it, but this time you construct a much better hypothesis and you hope that this time it will pass the test. Okay, so in the next lesson, we will talk about what science is, and just I want to give you a preview of what we're going to talk about in the course. You're going to learn things like the carbon cycle, greenhouse gases, and the greenhouse effect. You're going to learn about scientific concepts like adaptation, mitigation, exposure, vulnerability. These words you encounter almost every time you read climate change literature, so it's important to know what they mean. We're going to talk about the scientific consensus because there is a very high consensus among climate scientists that climate change is happening and we're making it worse. We're going to talk about future projections using something called the RCP index, which again, you'll find a lot in climate change literature. And finally, I will present some solutions because a lot of people say, oh yeah, we need to fight climate change and fight the good fight, but they don't actually finish the sentence by saying, what can we do to fix the problem? So I'm going to propose some solutions we can use to solve the problem. So stay tuned for more.